last video, we've actually covered the budget constraint and indifference curves. And we said that these are the tools that the economists use to describe a problem, how customer allocates funds between two purchases of two goods. And look, we stopped at the moment where we said the customer wants to be on the highest possible indifference curve. However, we said that the customer has only limited options by the money the customer has, as well as the prices of the goods chooses to buy. So look, what we arrived at is a problem that looks from a mathematical perspective like that. Find maximum of a function u, so utility function of the quantities of two goods that customers consume, right? Quantity of good X and quantity of good Y. And then under special condition, under the constraint that tells us that customer has a budget B, right? And the customer will spend his or her entire budget on either good X or good Y, right? And those are these are the quantities of those goods. And of course, given the prices of these goods. Okay, so look, what we should remember when we approach this problem is that in this case, this, and this is exogenous, in a sense that customer has no control over it. Well, you can speculate, how customer has no control over budget. Well, assume that you're at a store. At a store, you have a limited budget, right? You are limited by the amount of money you actually have. So this is the kind of situation that we are considering. We're not considering the situation when customer decides to just earn more money. And of course, prices of the two goods definitely beyond the control of the customer. So what the customer can only choose is the values of X and Y. So quantities of the two goods, and customer is going to do that in such a way that it maximizes his pleasure, so his total utility. Okay, so how do we approach such a problem? Well, we use the technique that we learned in mathematics class, and we reminded ourselves a couple of videos ago. We're going to use Lagrange Multiplier. So look, again, we start by making a very big Z, and we want to still maximize utility function with respect to X and Y. However, we are going to introduce the constraint into the values from which we are choosing. So here we have Lagrange multiplier lambda b minus px times x minus py times y. I hope you know how I got it. All I did is that I took this and subtracted from both sides of the equation, right? So remember, because b minus px times x minus py times y is actually equal to 0, look, all that we did at this stage is that we added 0 to the original utility function, right? And multiplied by some unknown constant. right? In this case, this is the same function. As long as the condition holds, this is 0, and we are imposing the constraint. Okay, but of course, in order to find the maximum, we're going to start with first order condition. First order condition, as usual, is telling us to take this function, differentiate it with respect to all the variables we've got here, and the two that we are interested in are x and y, of course, but we also need to introduce lambda because we are introducing the constraint, right? So, what do we get? First, we differentiate z with respect to lambda, and look, of course, out of this is the coefficient of lambda, right? So, this is all we have. And look, this is nothing more, of course, than the repetition of the budget constraint that we had at the very beginning. So, we can be sure that when we solve this system of simultaneous equations that we're going to get out of the three partial derivatives here, that this condition is going to be fulfilled. Okay, then, of course, we differentiate with respect to quantity of x, and look, we get out of this ux. Ux is simply partial derivative. Let's say that this is going to be our shorthand for partial derivative of u with respect to x, and similarly uy is going to be partial derivative of u with respect to y. So we got ux here, and look, x appears only over here, right? Except for the function, and so we differentiating this with respect to x gives us negative px times alpha, right? So we've got minus alpha px, and we equalize this with 0. And look, out of this we get that ux, so marginal utility with respect to x is equal to lambda px, or that lambda is equal to ux over px, right? So now we need to finally differentiate with respect to y, and then we get, of course, similarly marginal utility with respect to y minus lambda py equal to 0. We get out of this that uy is equal to lambda py, and out of this we get that lambda is equal to uy divided by py. Okay, and look, this result is something that we can use, right? We can compare those two because we got expression for lambda twice. So lambda equals lambda. Of course, we must get that the two are identical. So we got that this is ux over px equals to uy over py. And look, I can multiply both sides by px and divide both sides by uy. Look, what am I getting now? ux over uy. And over here, I'm going to get that this is px over py. And look, of course, I can multiply both sides by -1. They're still going to be equal to one another. And I'm getting over here and the two expressions that we see over here are actually things that we already know. Negative ux divided by uy, this is nothing more than marginal rate of substitution, right? This is simply the slope of indifference curve. And over here, negative px over py, this is nothing more than the slope, slope of the budget constraint. And look, this is actually the equilibrium condition that you're gonna discuss in detail in intermediate microeconomics. This is the condition that is allowing us to make a proper graph and show how does the customer maximizes his or her utility. Okay? And now we can demonstrate it using a graph. Okay, so we get here quantity of good. Y, quantity of good X. And let's start with a budget constraint, right? We remember that the budget constraint that we had was given by px times x plus py times y, right? So we know that if the customer spends her or his entire budget on good y, they're going to buy b over py. If they're going to spend their entire budget on good x, they're going to be able to buy b over px, right? And the line that connects them is a budget constraint, right? We are assuming that we are seeing here a straight line, right? Okay. And we know that the slope of this line, right, is negative px over py. So negative of the relative price of two goods. Okay, and now look, there exists an infinite amount of indifference curve that the customers could be on. However, there are some indifference curves like those here that in cases of which the customer can be somewhere around here, right? But it still has more money and still can spend more. And we are assuming the customer spends entire budget, right? So definitely those should not be the one that the customer is going to choose, right? Then there exists some on which the customer would like to be. And we know that the customer would like to be on the highest possible. But what do we see over here? We clearly see that those two are too high. They are beyond the budget constraint. It means customer can't afford to be on any of these two indifference curves. So which is the one where the customer is going to land? This is going to be the highest attainable indifference curve for this customer. So this is going to be an indifference curve that is tangent to budget constraint exactly at a point where the customer chooses exact amount of X and Y for which his or her utility will be the highest achievable. So now we see that basically what we get is the point of tangency, right? We get it directly from this condition because look, this is the slope of indifference curve, right? Slope. Look, in case of this slope, it's a constant, it's a given number, right? Because a budget constraint is a straight line, so it has always the same slope. However, we said that marginal rate of substitution changes over the indifference curve, right? Makes perfect sense that the indifference curve is changing its slope, right? And as a result, of course, it's different at any point. And this is the only point at which of course, this indifference curve is tangent to the budget constraint. Okay, so look, in principle, what we've got over here should guarantee us maximum. If we look at this from economic point of view, right? We basically outline the entire logic of this model, and it makes perfect sense that this indifference curve is the best the customer can get on, so it should maximize his or her utility. However, there is a mathematical view of this problem, and this is something that should be done to make sure that this is a maximum and not, for some weird reason, a minimum. So, what we want to establish is that this point is customer optimum, which in this case requires that the points that we found using this condition are giving us a maximum. How are we going to do it? Of course, we need to use the second order condition. I'm more changed again because in order to get to second order condition, we need to get back to the issue that we started with. Okay, so we had this Lagrange function, and for this function we found those three first partial derivatives. Now, how does second order condition works over here? Well, we need to find ordered Hessian, right? How do we do it? Look, let me just remind you once again that you can always think about rows in this bordered Hessian as being associated with three derivatives that we had, and then we are differentiating in each next consecutive row first by lambda, then by x, and then by y. Okay, because this is a Hessian, we of course remember the property that it is symmetrical with respect to principal diagonal, so we know what to expect and we will simplify as much as we can. Okay, look, let's start with this. So the first partial derivative, we see that this is simply the repetition of the constraint. We differentiate it first with respect to lambda, but there's no lambda, so 0. 0. Then with respect to x, it's negative px. And then with respect to y, we get negative py. And look, even without any calculations, just because those two expressions are here, I know they will be over here and over here. But let's check. Okay, first, I differentiate this with respect to lambda, I get negative px. If I would differentiate this with respect to lambda, negative py. Of course, everything makes sense. Now, the next step. Look, the next step is a little bit a little bit more delicate. So let me introduce it first a little bit. So look, here we've got a utility function. Look, this utility function is a function of quantity of good x and quantity of good y. And now look, if I'm going to differentiate a u with respect to x, right? I'm going to get ux by definition. And if I'm going to do this with respect to y, I'm going to get u, marginal utilities. However, look, even though this is marginal utility with respect to x, this function is a function of x and y. And the same goes over here. What do I mean by that? Look, imagine that our utility function has the form 3x squared y 2. Right? What is marginal utility of x? Marginal utility of x is 6x y squared, right? What is marginal utility? I'm sorry, what is marginal utility with respect to x? What is marginal utility with respect to y? Well, it's 6x squared y. Look, in both of these cases, we see that actually, even though this is a derivative with respect to x, it contains y. And look, I know that I shouldn't be even explaining that because of this, of course, is how those derivatives work. They need to be there. However, I know that once we introduce this notation, sometimes we forget that those are actually functions of x and y, and this will be very important later. So I wanted to make sure that we are on the same page with that. Okay, so look, the only thing that we've got to do now is to differentiate those two equations, first with respect to x, then with respect to y. So look, now I'm differentiating marginal utility with respect to x with respect to x, right? So I'm going to get uxx. And look, what does uxx means? Of course, as you can imagine, uxx is second derivative of u with respect to x. And, you know, by the same token, we will have uyy, which is second derivative with respect to y twice. So this is what I'm going to have if I'm going to calculate derivative of the last equation right here, right? However, we will have also cross derivatives, right? Because I need to differentiate this with respect to x and this with respect to y. But based on Young's theorem, we know that uyx and uxy are the same, so let's call them both uxy. Okay, and we just remember that uxy is a cross derivative. this, what was the condition? Oh, there is one more trick I wanted to tell you about. How can we simplify it? Look, there's a very simple way to get rid out of one more unnecessary thing, and those are the minuses here. How do we get rid out of them? Well, if I'm going to take -1 out of this row and out of this column, right? -1 times -1, 1. And this is our order hash. Now, we need to know the sign. If and only if this is going to be positive, we can be 100% sure that we are dealing with maximum. Yeah, so let's calculate. Okay, look. Here we have 0, and here I have that. Px, uxy, py. Py, px, uxy, right? So we've got this expression twice. So we've got 2 times px, py, uxy, right? We have this twice. Okay, what else then we have? Then we need to subtract py times uxx, py times py, right? So here we have a py, negative py squared ux x, and then we need to subtract 0 and uyy times px squared. Okay, now, what is the sign of this expression? We know it needs to be positive. Let's go step by step. Look, prices, of course, are positive. So this expression here is positive. We know that this expression here is positive. We remember about the minus, of course, and this one as well, right? Price not only is here positive, but it's squared, so it's double positive. Right? We can be 100% sure. Then, what about second derivatives of u with respect to the same variable twice? Look, we remember that marginal, the total utility looks like that, right? We remember that marginal utility looks like that, right? This, in other words, would be ux. I'm sorry, u. This is ux. So, the slope of ux is measured by uxx. And look, we over here can clearly see that the slope is negative. So it needs to be negative. And look, it is what we already said before. It's because of this decreasing marginal utility, right? When we consume something, each portion makes us happier, but each additional portion a little bit less happy. And this is captured by second negative derivative. And of course the same is true for y, right? So look, we get that those two that we see over here must be negative. And look, minus, 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 minus. So, out of this, we get that this whole part of this expression is definitely always positive. The only thing left is this. We don't like this expression. Why we don't like it? Because we don't know. Look, this expression captures a relationship between the two variables. It captures complementarity and substitutionality between the two goods. However, prior to actually having two goods that have their specific characteristics and relationships between them, we cannot say what is the sign of it. So look, this actually complicates our situation very much because, look, this is the only expression that we cannot determine the sign of. The rest is the way it should be, right? However, it turns out that there is a trick. A trick to solving this issue. And the trick resolves around going back to indifference. What do I mean by going back to indifference? Look, maybe the answer to the question can be found in the slope of indifference curve in a way how it's how it should look. And look, I can already tell you that it is, but in order to arrive at this, we need to get through a couple of very tricky steps. So let me just focus on the math of what we're going to do now, and I'm going to go back to economic interpretation at the very end. Okay, so look, what I'm going to do now is that I'm going to find second derivative of the slope of indifference curve, right? So what am I doing, right? I'm differentiating with respect to x, right? Because we draw them in y space. The slope that we found to be negative ux, uy. Okay, and look. First problem, we've got a quotient of two functions. What do? Of course we use the quotient rule. The quotient rule, remember that derivative of a quotient is equal to f prime of x times g of x, minus f of x times g prime of x over g x squared. So look, we need to do the same thing here, right? We take minus a constant up front, and also up front, let's just take this. So 1 over uy squared. Actually, we know that this expression is always negative, right? This is always positive because it's in square, and we've got minus in front. Okay, and then what are we going to have inside? Okay, so first thing, we need to differentiate x, right? Ux, right? So what is this ux over here? Ux, a derivative is our marginal utility. Oh, I deleted it. So, but we remember that if I'm going to differentiate it for a second time, I'm going to get u xx, right? However, because we're going to use here a certain trick, let me keep it simply as dux dx. Okay? And of course then we multiply it by uy. And then we subtract f of x, so our u of x. And now look, the next thing we need to do over here is to take derivative of the bottom. But look, uy, and we take derivative out of it with respect to x. Okay, so now that we dealt with the quotient, we might move on. Okay, this expression still is not very pleasant. Let's go over it. And let's start over here. Look, let me remind you once again, you're probably kind of bored with that u is a function of x and y as well as all its derivatives, right? So look, ux is a function of x and y, right? So differential dux, so change in marginal utility with respect to x can come from two sources, right? Uxx dx, right? So partial derivative with respect to x times change in x plus uxy dy. So partial derivative with respect to y times change in y, right? And now look, if I'm going to divide both sides of this expression by dx, I'm getting that dux dx, as you remember from our talks about total derivatives, is equal to uxx, one derivative, plus uxy dy dx, a product of two derivatives. So look, I can substitute this over here. And similarly, over here, look, duy, so change in marginal utility of y must be equal to dxy dx plus uyy dy. Dividing both sides by dx gives us duy dx equal to uxy plus uyy times dy dx. Okay, so next thing I can do is to substitute, right? Okay, so I will have now, instead of this expression, I will have this expression, okay? So negative 1 over u squared y times uxx plus uxy dy dx times uy minus ux times, and you will now have this expression. So uxy plus uyy dy dx. Okay. Now, it still might not look like much, but we are getting very, very close till the end. Okay, and what is this end? When we discuss Hessian, of course we discuss values of the Hessian at a certain specific point. What is this point for us? Well, our customers' optimum, right? And what was the condition for this optimum? Well, we said that in optimum, derivative of both indifference curve and budget constraint are the same. Right? We can use it as we know that this is what happens in equilibrium over here. Okay, so first thing that I can do is to substitute dy dx with negative. I can divide dy dx with negative px py, right? So let's do this one first, right? So I can take this and I can substitute it here. It's negative px py, and over here. Okay. Then I can do even more. Okay, but because look, again we are in equilibrium, right? So we know that this condition holds, right? So if this condition holds, this means that negative ux over ui is equal to negative px over py, or that negative ux is equal to negative px py times ui. So what I can do over here is replace this expression by negative ui px py. Okay, so what am I going to do now? I'm going to take out of this entire expression 1 over py squared. Okay, don't worry, we're getting closer to something that's gonna make sense. Okay, we got 1 over uy squared py squared. Okay, now what are we going to have inside? This, right, we took 1 over py squared. This is going to turn into uxx py squared. This one is going to turn, this thing is going to turn into, into negative, into negative uxy pxy py times uy minus minus uy, and now look, this one is gonna turn, so we are introducing, oh Jesus, this is gonna be long. And now we are introducing here this y, multiply everything by y squared, so we get negative y px, times u x y p y minus u y y p x, yeah, px, justice. Okay, then when we find, we need to multiply everything out over here. However, there is one trick that we can use before, so those two cancel each other out with the uy square at the bottom, right? Already a little bit easier. So what do we get over here? This is negative 1 over marginal utility with respect to y times price of y squared. And now look, okay, this will stay the same. However, here we can multiply everything out, right? So we will have negative pypx minus, so plus p squared. Okay, and this starts to resemble something that we've encountered here, right? Because look, what do I get here? I got a minus, right? I got a minus at the very end. And maybe let's just say I'm not a big fan of this minus. So I'm going to get rid of it, right? Which means that I'm going to change signs of everything inside, right? So what am I going to get? Those expressions are in pair, right? There are two. So we've got 2u xy px py. Then we've got minus, because right, remember we changed the signs. So minus uxx py square minus uyy px squared over uy p y squared. we say about this expression? Look, this expression is something you know very well. This is a Hessian divided by simply marginal utility of with respect to good y, which is positive, divided multiplied by price of good y squared, which is also positive. And look, by assumption, we said that indifference curve has a very specific shape. How do we call this shape? It's convex, right? Convex shape can be either decreasing or increasing, but of course we are interested in the decreasing part. But what is the thing about convex shape that we can be sure of? Well, it is that its second derivative must be positive, right? But look, we know that this is positive. We know that the slope of the indifference curve, the shape of the indifference curve must be convex, so it needs to be positive, which means that as long as the indifference curve we are using is convex, Hessian is definitely going to be positive, and this is how we can guarantee that we're going to have one solution that is actually a maximum. Okay, so now you get the entire process of how customer makes a choice about the quantities that he's gonna purchase given the budget and prices. Now, in the next video, we're going to make an example of how to use it. Look, I understand this is a lot of symbols, a lot of substitutions. However, again, as you will see, using it is extremely easy. Okay, thank you and see you in the next video.